And systems that fall into either the first case or the third case over here, they have at least one solution. And we have a name for systems like that. So that's the next definition. So a linear system which has at least one solution is said to be consistent. But as we've seen already, not every linear system has a solution. We've seen at least one example of a linear system that had no solutions. So that's also possible. So systems like that we say are inconsistent. So what I'm going to write here is I'm just going to say otherwise it is inconsistent. So I want to finish this section off with one more example which deals with the case that we have yet to see. So we haven't yet seen how to deal with a linear system that has infinitely many solutions. That's the only other possibility. So let's do one example that takes a look at that case, and that will complete this section. So here's the example we're going to do. So solve the system. And here is the system. The first equation is x minus y plus 2z equals 5. The second equation is 2x minus 2y plus 4z equals 10. And then the third one is 3x minus 3y plus 6z equals 15. Okay, so we'll start this in the usual way by writing out the augmented matrix. So let's start by writing down the augmented matrix for this system. Just turn each of those equations into rows of the coefficients and then the constant terms. So we're going to have 1, -1, 2, and then 5. That'll be the first row. The second row will be 2, -2, 4, and 10. And then our third equation will turn into the row 3, -3, 6, and then 15. Okay, so that's our augmented matrix. And what I'm going to do to start the solution off is I'm going to take this 1 that's up in the top left-hand corner and I'm going to use it to turn the 2 and the 3 below it both into zeros. So the operations I'm going to use to do that is I'm going to take row 2 and replace it with row 2 minus 2, row 1. And then I'm going to take row 3, I'm going to replace it with row 3 minus 3, row 1. And if you give it a moment's thought, you'll realize that those two row operations don't cause any conflicts with each other. So it's okay to do both of those row operations in the same step. Okay, so what would you have if you did that? Well, let's take a look. So the first row won't change, right? So I'm just going to start with a fresh copy of the first row. 1, -1, 2, and 5. So that's our first row again. Nothing's changing there. But now the second row will change. So I'll leave some space to do the second and third row. So let's fill out the second row. So if I go, I'm subtracting the first row from the second row twice. So if I go 2 minus 2 times 1, I'm going to get 0. -2 minus 2 times -1, that's like -2 plus 2, which will be 0. And then if I go 4 minus 2 times 2, I'm going to get 0 again, because that's like 4 minus 4. And then for the last entry, I'll have 10 minus 2 times 5, which actually is 0 again. So every single entry in this row turned out to be 0. And if you carefully work out what the third row will be, you'll get 3 minus 3 times 1, 0. -3 minus 3 times -1, that's like -3 plus 3, which is 0. 6 minus 3 times 2, that will give you a 0 in this position, and then 5 minus 3 times 5, sorry, 15 minus 3 times 5, that'll be 15 minus 15, which gives you 0 as well. So this is the first time this happened. You'll notice we actually have 2 rows of zeros, or which are sometimes referred to as 0 rows. So these two rows correspond to a very specific equation. So let's write that down. These two rows correspond to 0x plus 0y plus 0z is equal to 0. And well, pause for a moment and think, well, is there any value of x, y, or z that you could ever have that would ever make this equation not true? And the answer is no, because no matter what x is, this first term is just going to be 0 times x, which is 0. No matter what y is, this second term is equal to 0. And no matter what z is, this term is equal to 0. So no matter what, you have 0 plus 0 plus 0 on the left-hand side, which just evaluates to 0. And on the right-hand side, you also have 0. So this equation is vacuously true. It's true no matter what the value of x, y, and z, so it adds absolutely no information to this situation. So it actually is really just an empty statement, but it's true automatically, and statements like that in mathematics are called tautologies. So it's just a statement that is true just simply by the way it's been written down. It can't ever be false. So it's not particularly useful in this situation, but let's make a note of that, which is always true. So you can really just ignore those equations essentially because they don't add any information that helps you work towards a solution to this system. But what we do still have is the one equation that corresponds to the first row. Let's just jot that one equation down. It ends up being the same as the first equation from our linear system, but I just want to write down another copy of that equation. So we have it right in front of us, x minus y plus 2z equals 5. So really what this comes down to is just that one single equation. So how do you write down the solution to a single equation that has more than one variable? Well, you're not going to get a unique solution. Right? It's just not possible. There's many combinations of values you could assign to x, y, and z that would make this equation true. For example, I could take x equal to 5 and then take y and z both equal to 0. Right? I could also, if I took z equal to 0, and I took x equal to 0, and then I took y equal to negative 5, then the negative in front would turn this into a positive 5, and the other two terms would be 0, so that would work as well. But you don't want to just sit and now start brainstorming possible solutions to this linear system. You want to have a way that organizes every possible solution, and you can write it down in a systematic way. So we're going to do that using something called parameters. Really, it comes down to this. How do you want to describe the general idea of how to get solutions to this equation? Well, you've got three variables, and one thing that's definitely true is as soon as you know what two of those variables are, that will completely determine what the third variable must be. Right? And that's the idea, or that's the essence of this idea that the parameters are going to formalize for us. So here's how we're going to do this. And like several things in this section, we're going to talk more about this in section 1.2, but for now, this first section is more or less just kind of a preview of all the things you're going to see in the next few sections. So let's start by assigning parameters to y and z. So this is how you would do that. So we're going to let y, we're going to give it a parameter, which we'll use a new letter for. And you can use, in general, you can use any letter you like, but I like to use the letters S and T and U for parameters when possible. So let y equals s, and then let z equal t. So those are the letters I'm going to use for the parameters for y and z. And then now I want to actually really make it clear that these are parameters. So here's how I'll do that. I'll say where s and t are arbitrary. Well, first of all, I want to say that they're real numbers. So this is the way this would read. So let y equals s and let z equal t, where s and t are just real numbers, so they belong to the reals, and also they are arbitrary. And depending on whether you've heard that word before in ordinary language, its meaning might be different than than the meaning we use in this case. So what I mean when I write down the word arbitrary, what I mean is there's nothing special about the values of s and t. They could be absolutely anything, that as long as they're real numbers. And that's what I mean by parameters. So these are called parameters. Let me write a comment in blue here. These are called parameters. Okay, now those are just for y and z, but once I have parameters for y and z, once the value of y is set to be s, whatever that is, and z is set to be t, whatever that is, well then x is automatically determined from that. So what would happen now if I solve this equation for x? I would get x equals y minus 2z plus 5. Right? If I just bring the y and the 2z over to the other side of the equation, that's what I would get. And then now I'm going to go a step further and actually plug the s in for y and plug t in for z. And what you get is s minus 2t plus 5. So what we have now is we have an assignment for every single variable. We've got x given right here, we've got y given by this parameter s, and we've got z given by this parameter t. So what we're going to do now is we can now say what the general solution is. So the general solution is the bundle of all the possible solutions to the system that you could ever possibly have written in a package form. So the general solution is given by the following. So I'll write it in an ordered triple notation or point form. So I'm going to write my 3 coordinates x, y, and z for the first point. And then for the other point, I'm going to write now the 3 assignments to those 3 variables. So x is going to be s minus 2t plus 5, because that's what we got for x, right? That's what x was. Now y is s, so I'm going to write s next, and then I'm going to write t for z. Okay, and then for good practice, to get in the habit of making sure all the important information is summarized at the end, I'm going to finish this sentence and say the general solution is given by this assignment, where s and t are parameters, or you can write just s and t are parameters, or you can write, again, just say s and t in the reals are both arbitrary. And that's how you can finish this off. So that's what it means to write down the general solution to a linear system.